we now discuss the solution of a problem from the section analysis. The problem is on countable sets, and this countable sets is from the elementary set theory in the section analysis. This problem has appeared in CSIR National Eligibility Test held on 16th February 2022, and it is from the section B. The problem is, which of the following sets is countable? We are given four options. Option 1, the set of all polynomials with rational coefficients. Option 2, the set of all polynomials with real coefficients having rational roots. Option 3, the set of all 2 by 2 real matrices with rational eigenvalues. Option 4, the set of all real matrices whose row echelon form has rational entries. And we are given four options here, and we have to find out which one of them is countable. If we see these four options, and one of them is a very standard result, that is the option 1, that is the set of all polynomials with rational coefficients is countable. It's a very standard result which everybody study in their analysis course. So by looking at these four options, immediately a student will recall the option 1, and he puts that as option 1 is the countable. And I will show first how this option 1 is countable, the proof of it. Later I will show you options 2, 3, 4, these sets are uncountable. We now discuss the solution of this problem in detail. Let's take the option 1, the set of all polynomials with rational coefficients. Let capital P be the set of all polynomials with rational coefficients. Let P suffix n be the set of all polynomials with rational coefficients of degree n, where n is a non-negative integer. Yes, non-negative integer, because we have the polynomials of degree 0 also, which are precisely the constant polynomials. So we have to consider that also. For n is equal to 0, the set Pn is precisely equal to the set of all rational numbers. Why? When n is 0, we consider the set of all polynomials with rational coefficients of degree 0 with rational coefficients, means constant polynomials. So Pn is precisely equal to Q, where Q is countable set. Therefore Pn is countable when n is equal to 0. Now let's now take n be a positive integer. Then Pn is the set of all polynomials with rational coefficients of degree n, that is a0 plus a1x plus a2x square plus an x to the power of n, where each ai belongs to Q for 1 less than or equal to I less than or equal to n, but an not equal to 0, because we are considering polynomials of degree n. So, and Pn is equivalent to a countable set. What is that countable set? A0 comes from Q, A1 comes from Q, A2 comes from Q, and An minus 1 comes from Q. An comes from Q minus 0, because An not equal to 0. So therefore Pn is equivalent to Q cross Q cross Q cross Qn minus 1 times cross Q minus 0. So that is each one is a countable set. Therefore this cross product is also countable. Therefore, Pn is equivalent to this countable set. Now, what is P? P is the set of all polynomials with the rational coefficients that will be equal to the union n is equal to 0 to infinity Pn. That is, when n is equal to 0, set of all polynomials of rational coefficients of degree 0, degree 1, degree 2, so on and so forth. Sigma n is equal to 0 to infinity Pn is countable. Why? Why? Because when n is equal to 0, Pn is countable, and when n is equal to 1, 2, 3, so on and so forth, Pn is countable. Therefore, it's a countable union of countable sets. Therefore, this union n is equal to 0 to infinity Pn is countable, thus P is countable. Thus, hence the result. Thus, the set of all polynomials with rational coefficients is a countable set. So that's our standard result and its proof. And the answer is option 1 is the countable set. So for all, no, the question is in fact over, because we have already identified which is the countable set. But however, I'll show you the other options where I'll show each one of them is uncountable. Let's get into the next discussion. Now we consider the set of all polynomials with the real coefficients having rational roots. This is option 2. So let script P be the set of all polynomials with real coefficients having rational roots. Agreed. We consider S be the set of all polynomials of degree 1, okay, with real coefficients having a root alpha, where alpha is a given fixed rational number. So that means S is equal to the set of all R times x minus alpha. R times x minus alpha will give you all polynomials with real coefficients of degree 1 having a root alpha, where alpha is a given fixed rational number. Therefore, S is set of all R times x minus alpha. R belongs to R star, right? R minus 0. Then in that case, our S is contained in P, script P. Note that S is equivalent to R star, where R star is uncountable. R star is same as R for all purposes of deciding the uncountability. So R star is uncountable, and hence S is uncountable. Why? Why? S is uncountable. S is equivalent to R star, and R star is uncountable. Therefore, S is uncountable. Right. Now, S is contained in P, and where S is uncountable, therefore P is uncountable. Why? Because every superset of an uncountable set is uncountable. Therefore, P is uncountable. That is, the set of all polynomials with real coefficients having rational roots is uncountable. Okay, let's move to the next option. Option 3. The set of all 2 by 2 real matrices with rational eigenvalues. Let script M be the set of all 2 by 2 real matrices with rational eigenvalues. Let us consider the set S consisting of 2 by 2 matrices whose first row is alpha R, 0, second row is 0 beta, where R belongs to R, where R is any real number. And alpha beta are given fixed rational numbers. They are given and it is fixed. That means for all the elements of S, alpha beta are the eigenvalues. Why? In this, each matrix is an upper triangular matrix, and the diagonal entries are the eigenvalues. Therefore, alpha beta are the eigenvalues for each of the element of S. Now, alpha and beta are the rational eigenvalues of each matrix S, because each matrix of S is an upper triangular matrix. And further, S is contained in M. S is contained in M, properly contained in M. Note that S is equivalent to R, where R is uncountable. So how many such matrices will be there? As many as there are the R, because alpha, beta are fixed and 0 is fixed, and R is varying. R is varying. Therefore, how many elements will be there in S? As many as there are in capital R. Therefore, S is equivalent to R, and where R is uncountable, therefore S is uncountable. Now, S is a proper subset of M, and S is uncountable. Therefore, every superset of an uncountable set is uncountable. Therefore, M is uncountable. This implies the set of all 2 by 2 real matrices with rational eigenvalues is uncountable. We now go to the next option. Option 4. The set of all real matrices whose row echelon form has rational entries. Let script M be the set of all real matrices whose row echelon form has rational entries. Let us now consider S be the set of all 2 by 2 matrices. Here the set of all real matrices, and what is the order of that matrix is not given. Therefore, it can be any matrix of any order. That means the set of all real matrices of any order. But now we consider S is equal to the set of all 2 by 2 matrix. First row is RR, second row is R times 2R, where R belongs to R, set of real numbers, R not equal to 0. Now, we ask the question, how many elements are there in S? As many as there are in R star. Now, we have taken the matrix RR to R. Now, we have divided the row 1 by R, each entry by small r, and divide each entry in the second row by small r not equal to 0, no problems. So that will give you 1, 1, 1, 2. Then from second row subtract R1. It's not minus 2R1, it is R1. It is R1. From R2 minus R1. So from second row subtract the entries of the first row. R2 gives R2 minus R1, not 2R1, R1. And it will be 1, 1, 0, 1. It is a row reduced echelon form with rational entries. All are rational entries. So thus S is contained in M, and note that S is equivalent to R star. I have told you how many elements are there in S, as many as there are in R star. S is equivalent to R star, where R star is uncountable, therefore S is uncountable. Now S is contained in M, and S is uncountable. Every superset of a uncountable set is uncountable. M is uncountable. Thus, the set of all real matrices whose row echelon form has rational entries is uncountable. So that's how we have shown options. The sets that are given in options 2, 3, 4 are uncountable, and the option 1 we have already given a proof that it is a countable set. That is the discussion of the solution of the problem from the section analysis. It's on uncountable sets. I hope that you have understood the solution of this problem. I wish you all the best. Thank you.